Pulling it that way, right on T2.
Any questions? Master set 23, number 8.
I suspect you're gonna have to handle 2 bars on that one.
It's 2 charges on a line. One is negative 8 coulombs to the right. 3 coulombs is at 0.
So I have 3 coulombs at 0.
Negative 8 to the right, 20 meters. No, that's the
To the
left.
right, the other way.
Your other right, yeah. Or 0.2 meters, I guess, it's 20 centimeters. No, wait, no, it's 20 meters.
20 meters.
Yeah. Says work an additional negative charge we put so the net force on it equals 0, but I don't know like what you're talking about. Like net force on what?
On the third charge.
On the 3 coulomb charge?
No, on the,
Oh, so the new charge that you put on there
Yes.
is 0? Okay,
on it referring to
okay.
the additional negative
For
charge.
some reason that didn't register in my brain.
Okay.
So it needs to go in between the 3 and the negative 8?
Well, if I put a negative charge here, then it's gonna be repelled by the 3 and attracted by the 8. Other way around. Put a negative charge here, it's gonna be repelled by the negative 8 and attracted to the 3. So it can't, there's no way that could be in equilibrium. Over here, it would be attracted to the 3, repelled by the 8. Over here, staying attracted to the 3, repelled by the 8. Definitely not here. But in terms of location, I know that this is a higher, this is gonna have a greater magnitude of force acting on the charge than this will.
Yeah.
Therefore, I need to be farther away from that in order for it to balance. That's gonna be over here somewhere.
Yeah. Yeah, I have it probably on the left, but that's all I got so far.
You could potentially just put it some generic spot. The 2 approaches are, if you set it up, you can just stick it some generic spot, you don't have to think about where it's gonna be located, just, it's some distance X from 0, so you can just say, it's some distance.
Yeah, because
X.
you don't give us the new charge amount, so
Right.
it could be closer or farther away depending on how big the charge is.
No.
No?
It actually not gonna make a difference. Because the forces, because remember that the force, magnitude of the force, K Q1, Q2 over R squared. Well, let's put it in terms of this, 1 and 3, and then I'll have K Q2, Q3 over R squared. The magnitudes will balance. Q3 is gonna cancel if you set them equal to each other.
Oh, because we're trying to get the F at 0. Okay.
Other way of looking at it is that the force on the third charge is going to be Q times the electric field, that's the third charge. And where the force is 0, equilibrium, the electric field would be 0 also.
Mhm.
And the electric field does not depend upon the third charge.
Yeah, that's the second part of the question, is talking about the electric field.
Yeah.
So you can take, where it says Q1, Q3, and then Q2 and Q3, you could, would it be both charges together that you're looking at versus the other charge? Yeah.
Alright, so let's say it's at some position X.
Yeah.
So I have, if that's charge 1 and charge 2. I want the total force on the third charge, would be the force on the third charge from 1 plus the force on the third charge from 2.
Mhm.
I'm doing the sort of the more formal math approach right now. I know the total force has to be 0, equilibrium. And so this is gonna be that constant, Q1, Q3, over whatever the distance between them is, squared, which would be X. So I do that. X squared, R 1 hat, plus K Q Q2, Q3 over 20 minus X squared R3 hat. So, in essence, we have two different references here. We need to get them in terms of the same reference. But I know the magnitudes have to be the same. So wherever it is, what's gonna be attracted to one and repelled by the other, wait, this is a negative charge here, oh, that's right, I'm gonna get a negative there. That's a negative number, Q3 is a negative number, so all of this will be positive. All of this will be negative. That's sort of irrelevant. What I'm getting towards, the magnitudes have to be the same. And wherever the location is, they have to be opposite sides. So if you set the two magnitudes equal to each other, K's cancel out, Q3's cancel out. Quadratic formula, or cross multiply quadratic formula, you'll get two answers. One of the answers is where the forces are opposite each other, and the other one where the two forces are in the same direction.
Okay.
Did I answer the question?
Mostly, yeah.
Do you want to ask it again?
Huh?
Do you want to ask it again?
No, it's okay, I think I'll figure it out.
Right.
I have a little more to go on now, and even just the fact that, now it clicks that, the force, we're looking at it on the new charge we're putting on there. Like I said, for some reason I didn't get that before, so.
Okay. I have the variations of the question where does the third charge need to go so that the force is on the first charge or in equilibrium, but not in that case. Other questions? All right, so let's take a look at electric fields. Last time we did a little calculus, and you're probably hungry for some more. Except we'll do a more difficult problem than we did before. This time, I'm going to establish kind of a distribution of charge along the y-axis. We'll give a total charge of 3 nanocoulombs. That distance from there to there, let's make that 4 meters. And I want to know the electric field here. Call that point P. So the electric field at point P. It's similar to what we were doing when we found the force from an infinite line of charge. If we put in limits of integration, this would be similar to finding the force from a finite line of charge. Well, we'll go through the process. I have a distribution of charge. I cannot make any assumption that this is a point charge. So I should give some distance here. We'll make that 2 meters away. Since I can't assume it is a point charge, well, there's no valid reason to make that assumption, I have to use calculus. And I start out by just picking some little bit of charge. I need to sort of create a point charge, and so this is the charge dq. This is positively charged, so I know that electric field is going in that direction. Generically, we always assume it's a positive charge. If I did not give you the charge itself, we can make the assumption that dq is positive, and then if it turns out that it's a negative that will come out in the math at the end.
So are you saying, okay, so that's from DQ, that it's,
Say it again?
so the charge is going down to the right from DQ?
The electric field is going
Yeah,
down
so
to the
the
right
electric field.
from DQ. All right, so I have the DQ, now I have to sort of create variables which should disappear in the end. I need some relationship there, that's theta. The distance from here to here, I'm just gonna label as y. Since I'm at the origin, doing that to y, no problem. This distance here, I'm just gonna make big R, and little r is the distance from wherever DQ is to wherever point P is. I know big R is 2 meters, but I'm just gonna use letters in it, because frankly, if I do some substitution in one place and non-substitution in another place, it just aesthetically displeasing, as I'm sure all of you can appreciate. Now that I've created a point, I can use a point charge formula. So it's gonna be K, so officially, the differential of the electric field at point P is equal to K dq over R squared.
Where's the R? Oh, right there.
Sort of highlight that triangle. So this triangle right here. My hypotenuse is R, the bottom leg is R, big R, and then the side is little y. All right, doing an integral with a unit vector in it is not particularly easy, because as dq changes its position, as y changes, r hat changes, so I have to get it in terms of something else. It is, that's a variable, that's a variable, that's a variable. I'm trying to get it in terms of a single variable. So I know that r hat is going in this direction right here, that angle is theta. And so r hat, if I go to the traditional I hat, j hat, r hat is going to be cosine theta, I hat plus sine theta, j hat. Now we sort of skipped this step yesterday, or some previous class. We sort of skipped this step because one of them was going to cancel out and we didn't have to worry about it. We just thought through it and knew we could get rid of half the problem. We can't do that here. We cannot get rid of half the problem. I did not state this, but if you read my mind, you got it. Uniform charge distribution. Uniform linear charge distribution. In other words, lambda equals cube over what that equals L.
L is the big line,
Yeah.
and Y is the small one.
Yeah. Y is the distance to where dq actually is. So this now becomes k dq over r squared cosine theta I hat plus sine theta j hat. It's a fun little problem. We're gonna have to we'll end up doing 2 integrals. One of which I suspect will be a u substitution, and the other one is gonna be a look up the table. Or look up in the table. If you don't like k, you can always use 1 over epsilon naught, 1 over 4 pi epsilon naught. All right, so I still have 3 variables here. I need to get in terms of a single one. Well, looking at my bluish triangle right there. So this is big R, this is little r, and this is y. That is theta. What is r in terms of, what is little r in terms of y and big R?
tangent?
I'm not bringing the angle into it.
Say the question one more time?
What is the relationship between little r, big R, and y?
Pythagorean theorem.
Yeah. R squared equals y squared plus big R squared. What is the cosine of theta?
Big R over little r,
And what is the sine of theta?
y over little r.
Alright, I can start making some substitutions here. Oh, I also have dq. From this right here, I know that dq is equal to lambda dy. Plug that in, I get k lambda dy over, I'm gonna put the intermediate step in, r squared times big R over little r I hat plus y over r j hat. So this becomes k lambda big R over r cubed dy I hat plus k lambda y over r cubed dy j hat. And then the last substitution, bringing the Pythagorean theorem into it, this becomes k lambda big R over y squared plus big R squared to the 3/2 dy I hat plus k lambda y over y squared plus r squared to the 3/2 dy j hat. All right, pause for questions and people to catch up in writing.
So on the first one, you had k lambda dy on the very first substitution.
Right.
Yeah. And then the next one, you had k lambda r. Can you
Oh.
say how you got the r instead?
When at this point I distributed, and so when I combine these two, I get k lambda big R dy over r cubed from that. And then distribute over here, there's no big R over here, so that's why there's no big R there. But I do have a y on top, so a y just up there.
Okay, and then the third one, the y squared plus r squared.
Yeah, I know that I have an r cubed here.
Oh.
I know r squared is equal to y squared plus big R squared. Or r equals y squared plus big
Yeah.
R squared to the 1/2. And so when I cube it, it gives it 3/2.
Okay, okay, thank you.
Yep. Other questions?
I know that one was off the master set. Master set, is this one also from the master set?
Not explicitly.
Okay.
It's the next thing I'm doing, however, there is a master set question that is very similar to this.
Okay.
In the chapter 24. All right, so now the electric field at point P is going to be equal to the integral of what I have over there. So I've got my I hat k lambda big R, k lambda big R integral of dy over big R squared plus y squared to the 3/2. Like I said, flip the order around, but thank goodness for commutative property of addition. Plus j hat k lambda integral y big R squared plus y squared to the 3/2 dy. We have it down to a single variable, limits of integration. What are the biggest and smallest values of y?
Or 0.
Okay. And those would have units of meters, but I'm trusting everything's gonna work out nicely, and so I'm just gonna throw units in at the end. How do we solve this first one?
Table.
Yeah. If you wanted to do it the math way, how would you solve it? Yeah, trig substitution. All right, but we're physicists, not math people. This Python rumor. You know, it's gonna go off memory, but that's probably not a good thing.
Isn't it a squared inside a square root of r squared plus y squared? Or am I wrong?
So it was the r squared on the bottom, r squared plus y squared to the 1/2, and on top, I was trying to remember if that was a y or an r. No, it wouldn't be an r. Y would make sense. So we check it.
Sure, I believe that's correct, but
They're on the wrong call.
So we've got, there we go. That r cancels out with one of those. We go from 0 to 4, and so now I have I hat k lambda over r, and 4 over 2 squared plus 4 squared to the 1/2 minus 0. This big R is 2.